Um, Today's topic is going to be about PID controller design, and we will also include the phase lead controller. Last week, we did actually design PI controllers and PD controllers. And as far as I remember, I've talked about the fact that they are not going to be optimal design methods. They are just here to introduce you to the concept of PI and PD controllers. Well, today we will give a better and a more found way of designing PID controllers. Namely, we will look at the pole zero cancellation method, which can give away much information about the system and controller design problem itself. But the actual way of designing it numerically would be the so-called tabulation method, which creates basically a table of data. And then we look at the optimal solution. We search for the table and we hope for a good PID controller, where good is in quotes, of course, because that needs a definition. What makes a PID controller good? We will be talking about that. But of course, now this week we see that we have some specifications given directly to us, like 10% overshoot and 4 seconds of settling time. When we combine these two requirements, they will give us basically the exact point on the S domain or on the root locus where we want to have 2 poles of the closed loop. And hopefully when we can achieve that, we want to push all the remaining stuff like zeros and poles other than these two complex conjugate pair. We want to move them away, basically, to have a dominant pole placement. We will be also talking about the PID controller design method, which is the Ziegler-Nichols method. But I have to warn you here that the Ziegler-Nichols method is actually something that you might want to use for nonlinear systems or for systems that are quite difficult. And when you're looking for an initial point that actually works, then you're probably looking for the Ziegler-Nichols method. And other than that, we will be repeating this discussion here for the phase lead controller. But in fact, the phase lead controller is not going to be different than the PID controller itself in terms of design strategy via pole zero or tabulation. So that's going to be some repetition there. But yeah, well, let's start off with the first design method, which is going to be the pole zero cancellation. And we have these specifications given to us, so let's dive into it. Now, since we know what the overshoot is, we can directly conclude what zeta should look like because we have a formula. I believe we had this last week. So it's going to be pi squared plus log overshoot squared, where the logarithm is basically natural log, so log 10 and log 2 are different functions in MATLAB. So this should give away what zeta is. Since we know that, we can use TS equals 4 divided by zeta times omega n. We can manipulate this so that we are calculating basically omega n. And here this should be TS. Since I have them written down like that, this should be automatically calculated here. So when I know zeta, when I know the settling time, 4 divided by the multiplication of them should give me the omega n value. So I know where I exactly want to place my conjugate pole pair on the S domain. So that's nice. Other than that, what I also know is I want to design a PID controller. And we have talked about the fact that the PID controller transfer function can look quite different from each other. One of the realizations or maybe constructions of a PID controller could look like this. Another one would be KD times S squared plus KP times S plus KI, the whole thing divided into S. Another one would be basically, if you do the math here, you will get this exact term here, which is more like it. Now, if you look at it closely, you can see that here we have actually a polynomial, a second order polynomial. And here we also have a second order polynomial. Basically, they are the same, but the representation here is that we are looking at the zeros of the controller, and then there's a pole at the origin. Since we've used the root locus method last week and the week before that, this makes more sense if you're looking at a root locus, because you know where you place some zeros or a conjugate pole zero pair, and then you have a pole at the origin. Do you add this to the system, since these are the dynamic parts of your controller? Then you end up with a new root locus plot, and then you can conclude what k value you need in order to assign the pole. But here, first of all, Z2 needs to be written down like conjugate Z1 if you're talking about a conjugate pole pair. So it's not quite that different. So you cannot have two different complex numbers. They should be conjugate pairs. So that kind of creates an issue. But for now, I'm not going to bother with that, but I'm going to use this representation. But when you use this week's code, when you're designing PID controller, you would be better off with these two representations here. They are basically the same, but they have advantages over the line 13 definition here, because you are looking at linear coefficients here. And since this is a controller, it will be multiplied with the system. The system has nothing unknown in it. The controller has all the unknowns. So their multiplication will just give you linear unknown coefficient polynomials, sort of. And then the right-hand side is going to be the same, because residue times the desired polynomial, which in fact is actually already known, 2 times zeta times omega n times s plus omega n squared. So we know what zeta and omega n is. So this is basically a known polynomial. But the residual polynomial will be an unknown polynomial. So you will end up in a linear set of equations. And if a certain thing can be linear, then we want to have that, because it will be much easier to analyze and solve such linear equations than nonlinear equations. But since we are going to use a pole zero cancellation here, I am going to drop these two for now, and I'm going to use this representation. Because I have to, because I'm going to choose one of the zeros of the controller. So when we talk about pole zero cancellation, the thing is that our controller structure does not allow us to get rid of or cancel any zero of the system, because our pole is fixed at the origin. So that is important. It means that we are trying to add some zeros to get rid of some poles of the original system of the plant. So our candidates are S at the origin, or S at the origin, S equals -2 and S equals -5. So I can choose Z1 or Z2 so that one of these three different poles can be canceled. So that's what pole zero cancellation is. So we place a zero of the controller right on top of the pole of the plant so that they will get rid of each other. Why would we do such a thing? Well, if you remember the fact that TS is equal to 4 for this case, you might pick up on something. Namely, if you think about it, this would actually give us sigma equals 1. So the real part, which is this here, or zeta omega n, which is also called sigma, that should be equal to 1. And I would rather have a root locus which starts from, let's say, -2 and 0, and they coincide at -1, 90 degrees and -90 degrees asymptotes. Then I would have a certain solution, because setting time equals 4 gives me exactly this solution on this root locus. But yeah, if I want to have that, I want to maybe get rid of S plus 5. If I do that, I'll get rid of that. And if you look at the root locus of the remaining part, you will see that it would be S and S plus 2. Then we will have another S, and we would add a 0, etc., etc. But sometimes when you look at the poles, you might want to get rid of some of the poles. And yeah, let's, for example, try to get rid of 2 and see what happens, because we will add a 0 and stuff like that. But we decide on the 0 of the controller beforehand. So I'm just going to choose this as S plus 5. Now, usually when I'm going to write the code, what I would rather do if I'm in an exam, for example, I would rather look at the structure of the controller, of the remaining structure, because GS S times S plus 5 is going to be the new plant, and this is going to be the remaining parts of the controller. Now, this looks like a PI controller, so I'd like to do KP and KI, and this would be much easier than anything else. So defining it like this would be the best way of doing it. But I'm still not going to do this for now because I don't want to confuse you. But this would be a much easier problem formulation than the one that I'm going to choose now. Just to remind you. So since this is the fact, since this is the controller, our unknowns are K and Z, and they should be real. Now, I am sure that they are going to be real because one of the zeros is real. So therefore, the second one should also be real to end up with real coefficients, and K should be real, of course. Now, what I'm doing is I'm adding S to the system. I'm adding S plus 5 to the system, and the original root locus is going to be updated. Then I'm going to look at a PD controller design. So actually, designing a PI controller is one way of viewing it, or you can add the S to the system and then view it as a PD controller design. Because I remember that last week I did something like this. I separated the PI controller, the PID controller into its PID and PD parts. So this could be one way of viewing it. So if you look close to this, this part is the PI part, this part is the PD part, and a PID part can be decomposed into its PI and PD parts. So that's quite interesting to know, because one zero is here, the other one is here, and one pole at the origin is here, and you will have a p-type controller. So knowing that can sometimes be very helpful, but let's go on. I am going to actually do everything accordingly from now on, because I've chosen one of the zeros at the pole -5, and nothing changes actually. I can go ahead and look for the closed loop transfer function. And we do this for the p-type controller too, so it doesn't change. And then we will look for the zero and characteristic polynomials using numDan. And then we have PCS. Now, usually when we look at a system, for example, this is a third order system, and our controller is a first order controller, we should have a fourth order closed loop. But that's not going to happen here because there's an internal pole zero cancellation. Namely, S plus 5 is going to vanish, S plus 5 is going to vanish. So you will have a first order controller, but a second order plant. So it's going to be a third order polynomial. So let me run this. And you can see it's not a fourth order polynomial as it should be, because there's internal cancellation. We have a third order polynomial. Therefore, I'm going to define S plus P is sims P real, because the residual polynomial is needed like that. And then the problem is going to be the coefficients of PDS S should be equal to the coefficients of the multiplication of PDS times PES, comma S all. And since we're at it, let's write down what the problem looks like. There we go. PCS, I'm sorry. There we go. Now, we can see that, I'm sorry, we can see that the first equation is a trivial equation, but it is necessary because it shows that the highest order terms are with the same coefficients. But other than that, we can observe that P is going to be equal to 1, which is nice. Then since P is equal to 1, we will have 3.862 and then 100K, so K can calculate from that. And we can again have what Z is, because yeah, we can calculate everything here. It's not linear, not the optimal way of solving this. And this was the reason why I would like to introduce you to KD and KP, or KP and KI, the PD controller design or PI controller design. If you do that, you will get a much easier one. Of course, if the order is not that high, like in this case, it doesn't really matter that much. But the higher the order becomes, the more complicated you will end up in seeing a problem here. So yeah, let's actually solve the problem, because we have equal amount of unknowns and equations. So what we can do is we can just look up what the solution looks like. Now, let's play, yeah. So we have KP and Z. So kval double sol.k. Then we have pval p zval z. Now at this point, we are actually ready to define our PID controller. It should be kval times tf and we know what the zeros are, so a little convolution would help here so that we multiply these. So we have zval here, the value of z, and then we have 1 and 5 because we've chosen 5. Yep. So this is our basically our controller. Then we have fs times gs, comma 1. And now from this point on, we can just gather some data like TSE, info.settling time, OSE info.overshoot. What else do we have? Well, let's create a figure. Let's have a subplot. This. And yeah, another one, another subplot. X label being time. Hold on, read on. Actually, we should maybe change it like this. So yeah. There we go. Now, let's save the handles here. Read on. Let's look for the step response. Y comma t. Step ts. And then plot x1, t comma y. K. Line width 2. Maybe display name. Yes. Then overshoot. Like that. There we go. Now, what I actually want to do is, since I know what I added to the system or the actual plant, I want to see the modified root locus. So the newly created dynamic parts added root locus. So therefore, I'm going to plot the root locus of GS. But what I need to do is I need to basically take the dynamic part of my controller. So if you're lazy, what you can do is you can just directly look at fs times gs. And when you're clicking on the root locus, you're looking for k equals 1. That's one way of doing it. Or you can drop the kval part, so the dynamics. You add the dynamics only, and then you look for k equals kval. So you can do both. I'm going to choose the second one here. But by that, I mean, this is the dynamic part. So one pole at the origin, 1, 0 at -5, 1, 0 at -z val. So that's going to be added to the system. And when I click on the root locus and try to come up with a k value here, I'm going to click for k val. So this is still possible. And whilst we're at it, let's also get the poles and zeros using PZMap in order to see which pole is where. So AX2, real part of poles, imaginary part of poles, and then, I don't know, something like this. The same goes for the zeros. Like this. We could also place in some S grid here, which shows the zeta. We have zeta and omega n, which shows us the zeta and omega n values. And yeah, that should be actually it. Yeah. Let's test this out. There we go. Now, yeah, we should maybe adjust the Y limit here. So what I can do is I can just give a custom Y limit here, minus 2.5, and 2.5 seems to be reasonable, so that it zooms in a bit more, as you can see. So yeah, there we go. Now, in terms of the root locus, you can see it's quite different because our original system had only 3 poles. One of them was at the origin, one of them was at -2, this one here, and one of them was at -5. Since we can add 2 zeros and 1 pole at the origin with a PID controller, what we did is we added just one of the poles at -5 directly to get rid of this pole here. And since we added the second pole, which is the controller's or pole or the integrator of the controller, since we added that to the system, the only thing that remained was to place another 0 and choose a k value. Now, we can see that, well, first of all, there's something going on here, because the zeta and omega n value is not correct. So that's something. So maybe we messed up something here. Let me check. 0 to 500. There we go. S squared plus 2 times zeta. Yeah, there's a problem here. Let's run it and it will update it automatically. Yeah, that's more like it. Now, interestingly, we did have a problem, an issue there. Now we can see that the pole at -5 is canceled out, but there's another cancellation which happens at the origin. So we are actually experiencing a pole 0 cancellation at the origin, which is not quite nice. But you can see what I've talked about earlier. I said that if we would have a pole at -2 and another pole at the origin, they would coincide at -1, and our real part would be equal to 1, which is the settling timeline for settling time equals 4. So we have to be on this line, and the zeta here provides us the necessary angle, and the intersection of the omega n and zeta gives us this exact design point. And if I look at this, this is going to be the k value that I'm trying to use for my controller here. So something like this. And of course, k val is equal to the exact same value. So that was the reason why I separated the dynamic parts from the gain of the controller, so that I add only the necessary parts to my root locus, and I end up seeing the same gain value on the root locus and on my controller. Now, this is probably the best way of designing a PID controller, because it gets rid of the unnecessary stuff and you end up in only two poles, which are the conjugate ones, so infinite dominance factor because you have nothing else to worry about. But that's not actually it, because if you look closer at your controller, you didn't actually design a PID controller at all, because your controller has a pole at the origin and a zero at the origin. So this cannot, of course, happen. You have to use min_real in order to see what is left. And you can see this is no PID controller at all. This is a PD controller. Now, the reason for this is we have to add a so-called 0 at 5. And you can see there's, of course, this 0 at -5. And then there's this gain because you're getting rid of the system's pole here. There's a pole zero cancellation. The second pole zero cancellation, which happens at the origin, is most of the time dangerous. In real life, that's not applicable. But since this happens on the controller itself, you're basically adding it to yourself and removing it to yourself, because the controller is the product of the designer. It's not the system's pole, it's not the system's zero. So this means that you should get rid of the cancellation and you should design a PD controller instead of a PID controller. So it seems like this system can be controlled with a PD controller with a pole zero cancellation at -5 and with a gain value of 0.0286, so that you can achieve this settling time and overshoot, or in other words, you can achieve this zeta and omega n value exactly. And this is the best case. You can see that the settling time and overshoot values are quite close. You have overshoot of 10%. The settling time formula has a bit of an issue on its own, but instead of 4, it gives out 3.5. If you remember the week where we discussed this, it has its own nonlinearity, so we're just happy with it to use it for reverse engineering, sort of. So this is basically the best we can get here, but this is not always the case. For example, we've canceled the pole at -5. If you try to cancel only the pole at the origin, you will end up in doing the same, because this is the same solution. So what we can do, we can just look for an alternative, which would be to cancel out the pole at -2. So I'm just going to copy this part here and then paste it here. And the case of -2, I'm going to examine what happens here. So if we are happy with a design here, we should actually design a PD controller. But we want to look for the cancellation at 2. So I'm just going to do this, and of course this, and maybe update the figure number, and maybe get rid of this. Yeah, I didn't change anything because, again, I'm just canceling one pole, which is -2, and I'm just updating that numerically, and we should be good to go. So this is another solution. Let's zoom in a little bit. It seems like we should zoom here with 2. So now we can see that this is another opportunity. And we again get the zeta and omega n point here. They should be on there. But we've canceled out this one here. So yeah, our poles at the origin reach these points. One pole is canceled by one of the 0 of the controller. Then there's another pole here, and then the other 0 is basically here. Now, this is not quite a good solution, because we can see that, yeah, this one here is at, where is it? It equals 1. So this is basically s equals -1. And our real part is also equal to 1. So they're basically aligned here, almost. And in terms of dominant pole placement, this is not a good thing. We've seen before that when we enter the dominant region, the behavior of the system gets messed up. It will change. It will dramatically change, actually. But if it's a 0, it's even worse than adding a pole at the instead of a 0, because the overshoot became much, much higher then. Now here, that's not quite the same because we have a pole and a 0 in the dominant region, so it depends on that. But ideally, they should cancel each other out, or they should be far away on the left. This is not both of the opportunities here, or possibilities. So therefore, this is not a good design. And it reflects on the step response here. We can see that 37 point something is the overshoot. So we have a high overshoot. We were looking for 10%. Our setting time is not 4, but 4.6, but that's not because of our formula, because the formula for this one, this setup of poles and zeros is not applicable, because it only is about these this pole pair here. And if you have something else like another 0, a pole, then it doesn't reflect that system, so you cannot use the setting time formula. So canceling poles and zeros, of course, fixes the structure of the controller, of the PID controller, and that's not always a good thing. You can see that on the right we have a bad example, on the left we have a good example. Here, this one works, but this one is not a PID controller, it's a PD controller. Here, the PID controller is not the best one that we are looking for. But we don't really have to choose the zeros on the real axis, first of all. So that's one thing that we should keep in mind, and that the PID controller, that it's a subdomain that we're searching for, because not all PID controllers have real zeros. They might have complex pairs as zeros. We didn't even check that opportunity. That possibility is not addressed here. And furthermore, we have fixed one of the zeros to 2 or 5, so that's even worse than that. So we're just getting rid of the possibilities. So there's another actually pole zero cancellation setup that I might want to look at, and that's actually going a bit further and canceling out both -2 and -5. So that's another thing. Since you have 3 poles, one of them is at the origin, I wouldn't touch that one. So I might want to get rid of -2 and -5 by just canceling both of them out. So you would see then this problem would be a p-type controller design problem, because it gets rid of the poles and zeros of the controller and the system. So we're left with nothing else than basically the following characteristic polynomial. So let me just get rid of this. Run it again. PCS. And you can see the characteristic polynomial is just this one here. Now, if I want to plot this using a root locus plot, which I can do, by the way, we don't need this part here. So let's just have a root locus plot on its own. Like this. So that's it basically. Now the other one is at 5. So I can just add the 0 at 5, 0 at 2, and pull at origin to the system and look at the root locus plot, because essentially I'm looking for a p-type controller. The only unknown here is k, which is the p-type controller. So is this figure 3? Yep. So let's run it. Yeah. And actually, I'm just going to copy this here. There we go. Now our design point happens to be here, but our root locus plot does not even enter the left half plane. it doesn't also enter the right half plane. It's just on the j omega axis, because this is the j omega axis. This is the origin. So this is a double integrator, because our controller itself had an integrator and the system itself had an integrator. So we have a double integrator here. And we had this coefficient 100. So 100k divided by s squared is going to be the loop transfer function, which corresponds to basically this one here, because this whole thing here is nothing but a cancellation. If you set k on it, you can see s plus 5, s plus 2, s plus 5, s plus 2, 100, and s squared. This is basically the loop transfer function. And in closed loop, you will end up in these closed loop characteristic polynomials. If you choose k to be anything, then you will end up in sinusoidal waves, because it's on the j omega axis. It's a pure sinusoidal. If k is equal to 0, you will have a parabolic output, because, yeah, 1 over s squared, the inverse Laplace of that is going to be something like that. Yeah. And we can do nothing about it. So this doesn't even seem to be an important case. But I just wanted to show you that you are not restricted to cancel out just one pole of the zero. You might want to also try two of them, which is not most of the time possible, but it's something that we might want to try sometime. So this is basically a controller design using the pole zero cancellation. So what we're going to do now is we're going to transition into tabulation, which means that I'm just going to copy the first half here up to this point, maybe. Create another script, run 2.m. There we go. But now there's no pole zero cancellation at all, which means that we are back to the most general case of a PID controller, K, Z1, and Z2, and nothing else. So, yeah, I'm not going to use this representation here, but I'm going to switch to KD, KP, and KI. So KD, KP, KI. So the controller does not look like this. It will look like KD times S squared plus KP times S plus KI divided by S. Now here, since there's no pole zero cancellation, third order open loop, first order controller results in a fourth order closed loop, which we decide on two of them. So we have to have A and B, a second order residue polynomial like this. So once that's done, I'm just going to hide this one here. And let's run 2. This is the set of equations that we should look at. Now we can see here, first of all, we have one more set of equations than the previous pole zero cancellation method. We can directly conclude what A is, which is 5. But other than that, we have B and then the 3 controller parameters. And so if you look at these 3 equations, we have 4 unknowns. Or if we look at these 4 equations, we have 5 unknowns. So it means that we have one more unknown than we have equations. So this brings up the following. If you have this sort of set of equations, it means that you have infinite amount of solutions. And this is why pole zero cancellation is that restrictive, because, well, we have infinite amount of solutions, but we're just looking at the one that has a specific cancellation somewhere. So it's quite restrictive. Now, what we're going to do is basically choose one of the parameters so that we can work with numerical stuff here. Now, before I do that, what we need to ensure for our family is that, or what this set of equations tells us is that when we solve these equations, or when we satisfy these set of equations, it means that for all solutions of this set of equations, there will be 2 poles or a pole pair at the exact point where it should be. So we are assigning 2 of the poles to the given zeta omega n. But the remaining two poles, the residue poles, and the zeros, we're not concluding anything now. We don't even know if the closed loop is going to be stable because that's not included in this set of equations. This is just to assign two poles accordingly to PDS and nothing else. If we can somehow ensure that A and B for the specific system are positive, and the reason why I tell this is basically we have a second-order polynomial, and if the coefficients of them are positive, the roots are going to be stable roots. So in order to ensure the closed loop stability, we have to conclude the A and B positivity. A on its own is a numerical value, which is nice, which will not change. So it's always B equal to 5. That's nice. On the other hand, if we want to have B positive, then Ki should be, for example, positive. And yeah, since I have one free parameter, what I can do is I can choose one of the parameters of the set of equations and solve everything in terms of that parameter. You could choose KD, KP, or KI, but I wouldn't recommend to choose B and A, because they are the ones which we use for stability. So yeah, we would like to change the controller parameter. So it's common to choose KI. You can choose KP or KD. It doesn't really matter. But let's assume that we are choosing KI. And the reason why we do that most of the time is there would be most of the time a direct relation between one of the coefficients of the residue polynomial and Ki. So therefore we have this relation here, which shows us that if Ki is positive, B is going to be positive. If I choose Ki positive and solve the set of equations in terms of Ki, then all those controllers will assign a set of poles to the desired point, and basically they will be stable in closed loop. So that's a strong assessment that we did here, because it eliminates the possibility of instability, which is nice. But we don't know about the residue poles, where they are, if they are entering the dominant region, if the zeros are entering, that we don't know. So what we want to do is we want to solve this whole set of equations in terms of Ki, and which is possible doing by pen and paper, by hand. You can just say, okay, this divided by 100, or basically 100 Ki divided by this value here is equal to B. You plug that in, you plug A equals 5, you just calculate Kp, and the same goes for this equation. You can come up with Kd in terms of Ki, and A is equal to 5, so we're basically at it. So let's let MATLAB do this, because we have a computer in front of us. Now, in MATLAB, when you solve, what you can do is you can just give the parameters that you want to solve and omit some parameters that you don't want to really solve, so that MATLAB can decide that is going to be the free parameter, and the other ones are necessary to solve by the engine here. So what I mean by that is we could provide A and B, so it will look up for A and B, KD and KP, and if we don't provide Ki, everything will be in terms of Ki, because Ki is missing here. So sol.A, sol.B, sol.KD, sol.KP, so let's see what the solution looks like. There we go. A was equal to 5. And then KD seems to be 35 Ki. Or is it actually B? Oh, so it's B. 35 Ki is going to be B. And then we have this equation and this equation, which gives us KD and KP, basically in terms of Ki. So here you can see everything is in terms of Ki, because that's the free parameter here. From this point on, there are two possibilities, but I'm going to show you the numerical one. Since you can solve A, B, KD, KP, everything in terms of Ki, you can plug that in and analyze the whole system and make stronger conclusions about the system's zeros, about the system's poles, and everything. But I'm not going to go down that route, but we are going to just plug in KI some values and look for the results and try to come up with the best solution that we can get. Now, since the whole PID design problem depends only upon one unknown, which is KI, this is actually quite strong if you think about it, because if you would use any other numerical optimization solver like fmincon or maybe genetic algorithm or anything else, you would define KD, KP, KI as unknowns, as parameters. So you would have x1, x2, and x3. And this would form a 3D space. And you would have a feasible region, and then there would be the optimal region. You might have global or local optima, etc., etc. But in this case, we are on a 1D space, on a straight line, because, and more on that, we know that it should be positive. So we are basically on in an interval between 0 and infinity here, because negative makes it unstable. So we're quite restrictive in terms of search. And this would be the easiest one because we need an objective function that kind of tells the story about settling time and overshoot, and we should be good to go. So before I move on, what I mean is we have a KI vector that can start with 0, with 0.1 steps, maybe up to 1. I will increase that, but let's stay with a just small vector here. So what I can do is I can just loop through it with ki vec, define ki val equals ki vec ith element. And now what we can do is we can use double and then subs and then sol.kp. Instead of ki, I'm going to plug in ki val. Hope that this makes sense. What I'm trying to do is I'm trying to plug in the ki value that I've chosen now. And well, I'm plugging it into kp because kp is in terms of ki. You can see everything is in terms of ki. So I'm going to substitute all ki's with a numerical value. Convert it into double because I want to have numerical values. I might want to call it kp val because that's what it is. And I might want to copy this for kd and kd val. Now, if we didn't analyze the stability of this set of equations and conclude that ki should be positive, we might want to also look for a val and b val, and then the roots of one a val, b val, so that would give us basically the residue poles, and then check for their negativity or if they're on the left half plane to conclude the stability, etc. But you can see that when we do a little analyze on the stability, and when we conclude that A is a certain value and B needs to be positive, and that gives us Ki positivity, we can just remove that stuff and don't even bother with that, because we know that this is in the stability range. So there will be no solutions that are unstable in this case. So yeah, that's nice to know, because I'm not going to bother with A val and B val. And since I know what the controller looks like, I can define the controller directly here. This is why we call it a numerical approach, because it's not an algebraic approach. I am reducing the search domain drastically, because it's not a 3D domain where there's instability. I'm just reducing it down to a 1D region, which is quite small compared to a 3D space. And I'm searching that space, quite literally. I'm just plugging in KD val, KP val, KI val. That creates my controller, my PID controller. And then I'm looking for the feedback, fs times gs, 1. And then I can also conclude what the step info gives me. This is quite handful, believe me, because otherwise you might want to look for the step response and then calculate the setting time and overshoot yourself. And that's not that easy, or you don't want to bother with that all the time. But we can ask for step info and it will provide us the necessary data here. And that's basically it. Now, the only issue that I have here is I want to tell MATLAB, or I want to calculate something that will both set TSE to TS and OSE to OS. What I mean by that is I know what the overshoot should look like. I know what the setting time should look like, and I want to basically accomplish both of them simultaneously. Now, if I would just care about one of these parameters, then I would just go ahead and maybe formulate something like, well, the absolute difference between TSE and TS should be minimized. So that would be one thing that I could come up. And this would be basically the objective function. So I have a 1D domain, KI-vec. Over this KI-vec, I would minimize E1. And that would be it. But the problem here is that I have E1 and E2. Basically, we have a multi-objective design here. So that's a bit of an issue here. So this would be E2. There would be the possibility of having OSE and OS difference. By the way, I'm storing it divided by 100 like a fraction. So I'm just going to divide it by 100 to match that. So now my issue is that I have E1, which should be minimized, and E2, which should also be minimized. And they should be minimized simultaneously. Then the other issue is that this is in terms of seconds, because this is a difference. This is in terms of fraction, or it's unitless, sort of. And I cannot really combine them. If I do that, it would not be fair, because this is in seconds and this is some other unitless thing, and it wouldn't make sense to combine them. But what I can do for now, I could display immediate results. For example, KI-val, KP-val, for some reason, KD-val, and then maybe TSE, OSE, E1, and E2. I could display this for all possible KI values in this vector or in my domain to see what I'm working with, basically. So let's do that. Let's pull them to the side. There we go. Now we can see that the first one is my parameter of interest, so KI. And then we have the both other controller parameters, KD and KP, or KP and KD. And then we have the setting time, which starts with 3.5 and drops down to 1.95. And then this is overshoot, 10%, 34%, 37%, etc. And then this is basically E1, which corresponds to the difference of setting times, and the difference of overshoots. Now you can see I cannot really combine them because, well, 0.1 is actually the value that I'm looking for. And you can see E2, the error, is equal to 0, which is nice. Whereas 0.5 seconds in difference in setting time is here. And if I combine them, if I, for example, add them together, it would look like 0.5. Whereas this one would also look like 0.5, but it has 34% of overshoot, and the setting time is a better value, but these are not the same. This one is usable, but this one is not. And of course, I cannot combine these two columns together. But what I can do, instead of combining them directly, I can convert them to be unitless to end up in relative errors. So it makes sense to look up what the actual value was, 4 in our case, and 0.5 seconds of difference for 4 seconds of nominal value makes more sense to compare to or mix to each other instead of doing it with different units and combining them. So what I mean by that is I could just divide this into TS and this one into OS. These are the specifications, by the way. Don't use TSE or OSE. It's quite different. That's experimental data here. And I just want to have these specifications because those are the valid values. So I would rather look at E1 and E2 in the sense of relative error instead of absolute, because now it's kind of a percentage. Now I can mix up percentages. I can see that there's 12% error here, whereas 0% error here. Then I have 240% error and, I don't know, 6% error, something like that. So I can now combine them And this combining is actually reducing the multi-objective design into a certain projection with a certain relation so that it is a Pareto optimization. And here the problem is how you are going to basically combine them. One way of doing it is to take half and half. So treat them equally. So this means that I want to optimize the settling time and the overshoot equally. I want to treat them equally. They're equal to each other. I care about them equally. So that's what I'm trying to say here. Or I want to prefer, for example, overshoot. I think that it's more critical to optimize the overshoot over settling time. So therefore, 75% should come from overshoot and 25% should come from settling time. The important thing here is that there's a relation, or this combination is not arbitrary. It's called the convex combination. And what we do is we choose alpha for one, and then 1 minus alpha for the other one, so that their sum is always equal to 100%, basically. 25%, 75%, etc., etc. If you have more than two objectives, like setting time, overshoot, and rise time for some reason, or some energy function, whatever, then what you can do is you can just come up with alpha 1, alpha 2, and then the third one would be alpha 3, and all alpha would be between 0 and 1. 1, 2, 3, doesn't matter. They would be between 0 and 1, and their sum, alpha 1 plus alpha 2 plus alpha 3, should be equal to 1. So it does seem complex, probably, but it's not, because what I really mean by that is it would just sum up to 100%. Like I might want to go for 25% of that, 25% of that, and then plus 50% of the third one. So you can see they are between 0 and 1, and they add up to 1. So therefore, that's what I mean by this whole thing here. So you can generalize this for higher dimensions, basically. So let's go with 50%, 50%, because it doesn't really make that much of a difference in our case. And therefore, our objective function, or the thing that we want to minimize, is going to be basically the last column here, which is the overall index that tells us how good a response is. So we needed kind of a indicator, an objective function or a cost function that tells us how good our response is. This response doesn't look very good, but it seems like we're improving if we have lower KI values. So this is what the whole thing tells us here. And what I can do is I can just come up with another plot. How many do we have? I don't know, 2, 1, 3. So I guess 4. So figure 4 can show us basically a plot of KI vec, the first column, and then maybe the last column. Before I do that, of course, I have to save this whole thing. What I can do is I can create a table and save everything into a table. That's why we call tabulation, because we're generating a table, basically. How many rows do we need to have? We have KI vec rows, because each row corresponds to a certain KI value. And how many columns do we need? Well, 1, 2, 3, 4, 5, 6, 7, 8. Seems like 8, but this can depend. This is just for debug purposes, by the way. You don't really have to save everything, but in the tabulation method, we like to do that in order to debug a bit better. So instead of displaying it in each iteration, what we can do is we can go to the ith row of the table and assign this whole thing to the table. And then we can show the table like this. Now, if you're not really familiar with the indexing stuff here, if you're just a bit lazy and have a good computer, you might want to skip that by using this method here. So you could just copy this whole thing like this. You need to initiate, of course, table with an empty array. So if you skip this, you can just do it like this. But you can see that MATLAB complains here that the variable appears to change size on every loop iteration. and pre-allocating would speed up your for loop a little bit. So if you have a good computer and if you're lazy, you might want to go with that. But if you're a little bit like me and want to have optimized code for some reason, even if it's not that important, then you might want to take this route here. So we can display this table here. I'm, by the way, spelling it on purpose because there's a table already in MATLAB, which is quite nice and handy sometimes, but I don't want to override that function or get confused with that, so I'm not using it. This is literally a MATLAB table, which you can also use, but for performance wise, we don't really need that, so I'm misspelling it here. So I want to get the last column, because that's kind of my costs or objective function, or what you would want to call it. So what I still can do now, because I'm looking for the minimum value, I can call the minimum function here of MATLAB on this last column here, and it would provide me the value and the index where this happens. This index here will give me basically the row that I'm interested in. So index comma all. So this is basically the optimal row that I'm interested in. And this is the whole table. So that's it basically. And what we can do based on that is we can plot the optimal value. So ki vec index comma val, I don't know, maybe red square, line width, 2, and that's basically it. So we can see we have this interesting shape here. We have this whole table here, and the best row seems to be the first row. Now, of course, this is not the ideal way of defining the whole domain, because I've just defined a vector that starts with 0 and ends up in 1. A better way of doing this might be to look up in a large interval, because we don't really know where the optimal solution is going to end up being. So therefore, what we can do is we can use log space, logarithmic spacing. We could start with -2, so 10 to the power of -2, which is quite small, and 10 to the power of 3, maybe 500 different values. And I don't really want to show this whole thing here. And maybe also not the row. I'm just going to look up the shape here. So let's run this again. Now you can see it will take some time now. And if I even want to increase it a little bit more, it will slow down. And believe me, I have a strong computer now here. So if your computer is a little bit old, or your MATLAB version is also a little bit old, you might want to struggle. You might going to struggle. Before that, this plot is not actually correct at all, because we've used logarithmic spacing for ki vec. So you should better go ahead and change the scaling of the current axis here to the x-axis scaling to log, so that it looks like this once it computes the whole table. This is more like it because we've chosen a logarithmic scale in the x-axis. This is quite different than the one previously plotted here. Of course, what we can do is, if you're a little bit picky, ki is the x-axis, in order to remind ourselves. Y label is basically the objective function, and title is going to be the cost function or objective function. Something like that. So, first of all, I'm interested in this slowing down a little bit. I'm going to focus on that. What we can do in MATLAB is we can check how much time it takes to compute a certain piece of code, and we do it with a tick and tock. Tick invokes the timer to start, and tock stops it and shows you the elapsed time. And let's run it here. And you can see it takes 2.97 seconds. If I increase it maybe twice and run it again, you can see it increases. And well, usually we want to check as much as we can. So like 10,000 points maybe is going to be a good thing because we want to be sure that we are getting good coverage in terms of the domain. Yeah, let's see how many seconds it takes to calculate that. And one question is why it takes that long to calculate this whole for loop here. And imagine if you would do it in a three-dimensional space, because if I'm defining 10,000 points, 10,000 to the power of 3 would be then the corresponding 3D space. I'm trying to look up this big of an interval here. So I guess 10 to the 4 and 3 times of that. So it's quite big. And this is exactly a minute now. And yeah, as far as the computation power goes, if your computer is slower, you will get a higher time here. So what is the reason behind that? Because if you think about it, we have an assignment here, and we pre-allocated the table, by the way. If you don't do that, and if you do the lazy way of copying and pasting it inside of the table, then what you're doing is you're copying in the memory too much, because each time you add a new row to the table, it needs to copy it. I don't know how MATLAB handles it behind the scenes. It might have a upper bound, and it might just want to optimize it so that not all copies are going to be, or not insertions are going to be copies. I don't really know how that strategy is handled, but we don't deal with that because we've pre-allocated our table and it doesn't grow. And that's not it. So we shouldn't have a time consumption here. This one is an algebraic one. That should also be not an issue. This is also a few CPU calls and nothing else. This is a struct call, memory read write, not that much big of a deal. This is step info. The data is there and it should not take that much. Feedback, again, the same. Controller definition, again, the same. And then we have these two lines here, and ki vec, and then the for loop. So you can see the for loop is not that complicated, but why does it take this long? Well, the answer is here. We are using the symbolic toolbox here, and the symbolic toolbox is a high-level, complicated thing, and it's not quite built for performance. And if you have 10,000 points, and if you're calling substitute, it undergoes some manipulations that takes some time because it is a high-level tool that we are using here. Now, if we are defining the problem, it makes sense to use this. But actually, here we're just plugging in a numerical value, and it doesn't seem to be working well with using subs here. And we can fix that actually. We can fix it so that it becomes faster. And well, instead of doing this, what we can do is we can just take this sol.kp. If we look at it, it's just something arithmetic. And computers are pretty good at doing this stuff here. Why does it take so long? It shouldn't take long. So we can fix this, and you know that this is just basically a straight up multiplication plus summation and nothing more. It shouldn't waste that much time. What you can manually do, if you have no clue, you could just go ahead and define a function that would return the value of ki. If you know what a lambda function is, you could just have ki and then, I don't know, this whole expression here. So let's call it temp. Then you will have temp as a function, and you can plug in the value, and it would take no time. So instead of doing this manually, you can ask MATLAB to do it. You can ask the MATLAB function, which is in the symbolic toolbox. And you could just ask this MATLAB function to convert this into a proper MATLAB function, like funkp. And you can create the same for kd. And we know what ki is. So yeah, instead of doing this whole thing here, I'm just going to copy this. kp-val and kd-val will stay. I'm just going to call this one here and nothing else. So kd-val, funkd, and there we go. I'm going to comment this out. And let's see how much time this one will take. So it was roughly a minute. Let's see how faster our code becomes. Now we cannot optimize further. And you can see it's a sixth. So it's 6 times faster and only takes 10 seconds, which is not that big of a deal. We cannot optimize upon that because we have to have the step info, which will have to solve the whole step response, look up the settling time and overshoot, and return it. So everything else is still quite fast, but this portion here takes some time and we have to deal with it. And 1,000 times that or 10,000 times that is unavoidable at this point. So yeah, instead of using subs because it's not necessary here, it's not optimized. What we should do is we should just get rid of that part and convert this into functions and use it like that. You can apply this to almost everything here, to A, to B, to KD, KP. In our case, we only need these 2 controller parameters, so I'm just using them, but you can define A, B, and all the other stuff like that. So all symbolic expressions can be converted into MATLAB functions, which is quite nice because MATLAB functions, and you can see funkp on its own too, are vectorized functions. And vectorized functions with a dot multiplication can deal with the whole vector. So what we could basically do is we could copy this ki-vec into kp-vec and kd-vec and just apply the whole thing upon a vector. And it would be even maybe faster. But then I have to, again, take kd, kp, ki and do the whole thing with step info. There's no vectorizing this, so I cannot become faster. So that's the only thing that I can do. Maybe if I'm too obsessed with it, I could maybe use some CUDA or parallel stuff, but yeah, that's overkill for now because one dimension, just wait 10 seconds and it will give you the result. And you can see we've improved drastically here. So enough with optimization in terms of performance. You can see, and I would highly recommend you to use this MATLAB function way if you have a slow computer during homeworks and stuff. So yeah, let's continue on our discussion. We were looking for an optimized controller, and yeah, it seems like this one here is the best controller that we can come up with. So let's maybe check out on that. Hold on, grid on would be nice. And let's see what the controller actually looks like. So I know what index it is. So I could just maybe ki-val equals ki-vec index. So this is going to be the optimal value here. There we go. Then I can just call this, the whole thing here. Or I can even use the table, but yeah, I'm lazy, so whatever. Now, let's take actually this whole thing here and create almost everything and see what the difference is, because we have addressed this problem before. It should be figure 5. We have TS and we have calculated TS, so no problem there. And we're looking for the root locus plot. We should look for the zeros. Now, I don't know what exactly the zeros are, but I could just manipulate this definition a little bit so that it would give me the same effect. I could leave it like this, or I could just divide it to kd-val, because I know that s squared plus as plus b should be the polynomial if I'm looking for zeros. So when I normalize with kd, I would be reading kd-val from the root locus plot back. Or you could just skip on that and read the value 1, as I've talked before. Yeah, other than that, maybe that's good enough. So yeah, let's run this again. and see what happens after 10 seconds, of course. There we go. Now, since we've seen that it is somewhere here, we could narrow the whole domain thing because we don't really need to do that because it's quite different than the all remaining domain here. And we have a little bit of an issue here, seems like. So why did that happen? It shows us something that's not correct, I guess. What seems to be the issue? Maybe it's this. I would say that that's the problem here. So it should come back here. Now, I could eliminate the whole domain where we have 10 to the power of 1, even down to 10 to the power of 0, because it seems like gridding this or tabulating this region here makes more sense. I would increase the precision here. But other than that, for now, the best controller that is obtained looks like this here. And I guess we would recognize it a little bit more. We have it here somewhere. Now, it's not looking like this. It's more like, also not this one, of course, but it looks like it's almost like this here. We could compare it to this one, but of course, not entirely. Now, we can see that there's an almost pole zero cancellation here. We would be quite happy if that would happen because that's on the dominant region. Actually, this pole pair is more dominant than our supposed dominant pair. And then we have a pole in zero in this region, which is not the dominant region. So it's quite nice to have this here. But you can see it's more of like a, well, it seems like a lead controller part. A pole in zero has kind of a lead effect here. But yeah, this is not the best solution that we can come up with. We see that the overshoot value is also a little bit messed up here. I don't know really why. Oh, because we're displaying divided by 100, which should not be the case here. That was in the table, not here. So we have 30%, 31% overshoot, which is quite high. And the reason for that is this lead effect or this pole zero here in the dominant region, because they shouldn't be there or they should be on top of each other. So that's the reason why we have high overshoot and it doesn't look good. It's a little bit better than this one here, nothing else. So as I've said already, we might be interested in 0 and 1 or 10 to the power of -2 to 0. So what I can do is I can decrease it a little bit because I checked it globally and I decided upon 500 points between 10 to the power of 0. Maybe 10 to the power of -3 because, yeah, a finer, better value should come up. You can see it's quite fast now, and we have an improved result. But this improved result is basically the result that we had already. It's an almost cancellation here. You can see it's not exactly on top of each other, but they are close enough. And the same goes for here. So you can see that there's also a slight kind of a circle motion going on here, but they are canceling each other out almost. So that is interesting to note because if you look at the controller, the resulting controller looks like this. And you can see that this is almost at the origin. The more I increase this lower bound of my KI VEC, the more this will tend to the origin. And you can see this is also almost at 5. And we can recognize the fact that this is the value that we came up when we were canceling s equals -5. So we've actually shown numerically that it can happen that pole zero cancellation can come up with optimal values. And you can see here are some different behaviors and stuff going on, but from this point on, we're basically tending to the optimal solution, which looks like global optimal, by the way. And it is. Yeah, and we've shown this numerically. So this is a very special example, therefore, to showcase you that sometimes pole zero cancellation can give you the best answer. But if that's not the case, this numerical one would come up with a solution that would have the best step info results like settling time and overshoot. But it still doesn't mean that we are talking about dominant pole placement, because as you can see, the numerical iterations didn't end up in dominant pole placements, because it tends to cancel poles and zeros or almost cancel them, and it's not pushing them away. So it's not the same thing. Therefore, we should be aware of both results. So we should be using tabulation methods in order to look globally to the problem with one domain approach, one D approach like KIVEC or KDVEC or KPVEC, whichever you choose. And we should look at it numerically. Whereas what we can do still, and which we didn't cover here, is we could look at it also more technically or theoretically. But that's another part that we are going to cover in the future. But you can see numerically we've proven that if something is optimal, it is optimal, and this system should actually, or it is sufficient to design a PD controller for this system, and a very special PD controller because it cancels out one of the pole of the system. And yeah, and it doesn't actually take that long if you think about it, and if you come up with this result or conclusion. If you can conclude that the best controller is going to be canceling out this pole here and not using a PID controller, but a PD controller, then you can see you just did get rid of this one here. You can just use the gain condition and come up with the overshoot value that you're looking for. So the distance from here, of course, the angle condition and gain condition in conjunction. If you're in an exam, you should just spot this valuable result here. Other than that, calculating it would not be that difficult if you know what you're doing. But of course, that's not most of the time the case. Pole zero cancellation is not always optimal, and probably not optimal at all. But this is a very special case to indicate you that pole zero cancellation might happen and might do the trick. The only issue that we would have with this controller or this setup specifically is the fact that the pole zero cancellation might not happen. In the real world, in our class, in MATLAB, in the symbolic toolbox and control system toolbox, everything is probably ideal and everything will happen. We are quite optimistic here. But if we are in a lab and if we're looking at a system, that's a whole different story. Even though we designed such a controller, we will basically not use KI here. It will be canceled out, and we will maybe struggle with these coefficients. And even when we don't, the model of the system will depend on conditions that we don't take into account here. The system is not going to be linear over all the input and output ranges. There will be so much stuff that we should worry about. Heating up the system changes the resistors and stuff like that, that changes the position of the poles by manipulating the whole model, because the parameters will change, the poles will move, and your pole zero cancellation will never be perfect. That's not possible. You can't have a system in real world that has exactly a pole at 2.0000001. That's not possible. It will be something around 2, but not exactly 2. And that's the reason why pole zero cancellation, on the other hand, is also quite dangerous. If you're somewhere at 5, and if the controller structure is basically canceling the pole zero, which in this case is not a pole zero of the system, this is a good example. This could be used in the real world application. But for example, this one can never happen in the real world. And you can see why, because there might be a slight tendency to the right half plane and a little parameter variation would end up in the right half plane, and your system will mess up, and it will become unstable. So pole zero canceling is not always a good thing, but it might be something like an adaptive control strategy or something like that. Then maybe pole zero cancellation is not that big of a deal. But usually you should be careful about this, and you don't want to be near the vicinity of the j omega axis because that's the most dangerous version. On the right half plane, you never pole zero cancel anyways because that's not possible. And it will definitely be unstable. So yeah, but you can see sometimes you have to do what you have to do. You have to cancel out the poles, and there we go. Of course, there's a difference between canceling poles and zeros in closed loop and in open loop, because this is a closed loop cancellation. This happens in the closed loop. So if it's near, then we are also okay because it will be a pole zero pair. And if it's out of the dominant region, that wouldn't affect the system that much. But if it's in the dominant region, it will mess up the system's behavior probably. And other than that, it might be even worse if it's an open loop control, because we're not measuring anything. So yeah. Now, when we design a PID controller, this run-to script here is quite a good example of how we design a PID controller numerically, because we have we reduce the whole problem from a three-dimensional space into a just one-dimensional space, which is quite powerful, and which is the difference and why we should use control system design strategies given here instead of blindly searching for KD, KP, and KI. So this is more powerful because, well, it takes too much time to evaluate this in 3D space as in 1D space. And this is not the only way of doing it. This is the numerical way, and which is called tabulation way. So now here we have the PID controller via Ziegler-Nichols. This is a whole different topic, but since it's about PID, I needed to include it. And it doesn't even rely on the stuff that we have here. For example, we don't really care what zeta overshoot or whatever these other stuff look like. We just care about the transfer function, because what we need to do is we need to look for a special property of the system, which is basically the exact gain and frequency or period where marginal stability happens. So we're going to search for marginal stability, which means that I'm going to define a p-type controller and then look for the closed loop, which would look like k times GSS divided by 1 plus k times GSS. And then we're only interested in PCS, so I'm not going to bother with the other stuff here. And we're interested in the point where basically the root locus, therefore I'm going to also plot the root locus here, figure 5. So let's have figure 6. So we only need the root locus of GS actually, but I'm also going to acquire the data numerically here. So we're looking for the j omega axis crossing. Therefore, we're looking for a root that looks like this. So I'm going to substitute PCS, a root that looks like 1i times omega, because j omega, s equals j omega, is a root on the j omega axis. The only thing is I don't know where this crossing happens, so therefore I have unknown omega, but it's going to be j omega, and its symmetric conjugate will be minus j omega. So there should be a j omega pair that crosses through the j omega axis. And if it's one of the closed loop poles, it should satisfy the characteristic polynomial. It should be the root of the characteristic polynomial of the closed loop. Therefore, the problem that I'm going to solve is just the real part should be equal to 0, because it should satisfy the polynomial since we're dealing with complex numbers. And same goes for the imaginary part. It should also be equal to 0. Then solve it. And probably what I need here is k-val. So let's convert it to sol.k. And we also need omega val. And if we display them, we will see that there will be some solutions which we're interested in, and some which we're not interested in at all. So like 0, 0.7, which is the same gain, and 0 and 3.16. So basically we are looking at this root-locus plot here, and we're interested in this j omega crossing. And yeah, we could eliminate that. Let's maybe do it. The index is going to be omega val greater than 0, 0 not included. So k val is equal to k val index. Same goes for omega val. Now from now on, I need k critical, which is k val itself, but omega val is 2 times pi divided by t critical. So this would be then 2 pi divided by omega val. And we're basically there. 0.6 times k critical should give us kp. Hope that I'm not wrong. And I don't remember k, it's probably kd. We'll see. Should be kp divided by 0.25 times t. I don't really remember. Times t critical, and ki is something like 0.125. Something like this. I will look it up if it's not working. And there we go. You have the controller. So this is an interesting thing, because it's not looking at the model if it's a certain order of a model, what the poles are, what the zeros are. We are not really interested in all that stuff. All that we are interested in is how it behaves during marginal stability. Here, t critical is basically the sine wave that we have, and its period. And we're looking for that period, and we can obtain it from directly using this approach here. And we can get the value that results in this marginal stability behavior. And we're using a table, which I just magically wrote down here. Hopefully I'm not wrong. And then we have the system. So that's the only thing that you have to do for the Ziegler-Nichols method, which is quite easy. Let's us basically take this part here, plug it in here, and then maybe the step response part. All zeros maybe could be helpful. So figure 7, I believe. Yeah, there we go. Now, root-locus doesn't make that much sense anymore, so I'm not going to do that. But poles and zeros are going to be placed, settling time, stuff like that. Hope I'm not wrong. If I'm wrong, I have written it down in the PDF. So yeah, it seems like we messed up, by the way. Yeah. Let me just quickly do this because I'm just showing the S grid here. I might want to use this. Yeah, and it doesn't even relate to Z10 omega, and it doesn't have to do anything with that. Therefore, we can just go ahead and not even use S grid at all. So this is not relevant data here. Was it 0.5? I guess it was 0.5. I'm not quite sure. The shape doesn't look like it. It doesn't also look like it. I might want to need to look up it from the PDF. But this is basically the whole story. You have a table which gives you basically the PI controller, the PD controller, or the PID controller with Ziegler-Nichols. And you only have the input parameters KC and TC, which are obtained from the marginal stability of the system. Now, theoretically, using the Ziegler-Nichols method is actually for cases where PID controller design is quite hard, for like nonlinear systems, or probably also maybe for very high order systems. That could also be an application case. But this is a powerful tool if you think about it, because you don't really care about the whole system. You just look for the marginal stability and you come up with certain red values from it, and then you use them from a table. And if you think about it, if you have a nonlinear system, or if you have an optimization tool and you want to start with a certain PID parameter set, this is the best strategy to start with, because it gives you a PID response that has stability and it has a certain performance. And then you might want to try to optimize starting with this response, for example. So that's why we should probably use it. And if you think about a black box system in the laboratory, and if you have, in the old days, we had oscilloscopes. Nowadays, they are more digital and stuff like that. But if you have an oscilloscope and if you just increase the gain, which is our controller in this case, and once you spot this marginal stability behavior of the system on the oscilloscope, then you can just use some measurements which correspond to KC and TC, and then you can just design your controller and try to apply it to the system. This is where the power lies in Ziegler-Nichols. We in our course, of course, cover this method like this, but the actual application should be in the laboratory because, well, this is more of an experimental design method or tuning method. Therefore, it makes sense to see the power in act, maybe. So think about the Ziegler-Nichols in this way, so that it is an experimental design tool that most of the time is used to start to search a good PID controller. This would be probably an initial point for a PID controller, and then you would look up a better one or try to improve upon that. So yeah, I'm going to cover this in the PDF again. Now, when you are going to design a phase lead controller using pole zero cancellation, you again have the same opportunity where you can get rid of S+2 or S+5. And since it's just going to be a phase lead controller, you don't really have to even do stuff like adding another pole or stuff because, well, PD controller is also a lead controller. So technically, our best controller ended up being a PD controller, and directly by getting rid of S+5, so K times S+5 is a lead controller, a special version of it. You could just apply that, and that would be also the answer to D. And if you are going to use the phase lead controller via tabulation, it's again the same procedure. So A and B are basically the same with D and E, where I just go ahead and change the controller structure in run one. So you come down here, you look up the controller structure and say, of course, I have S+5. So get rid of S+Z and add S+P. So K times S+5 divided by S+P would be a general way of defining a lead controller. And then the same script would be run here, and then you would just end up having a result. If it works, it works. If not, then it doesn't. And the same goes for tabulation method too, because we're just going to give the structure, look up the closed loop degree, define the according residue polynomial, and then the same goes on like this. So for different controllers, this doesn't really differ. It's going to be the same. Pole zero cancellation and tabulation. It only depends upon the structure, the result, if it's optimal or not, if it's improvable or not. That's another thing. Commenting on it will change, but other than that, the steps are the same. So therefore, what we can do is, before we conclude today's lesson, we could just look up the PDF and see if it's going to be different or not. By the way, in this lesson, I have basically created a quite good tabulation method code in MATLAB. That's not available in the PDF because here I have shown you the bad method of doing things instead of the best way. And I didn't really fix up on that because, yeah, you should at least try to code it once so you get the grip of it and see what the difference could be really here. For pole zero cancellation, of course, if I'm in an exam, I would like to just update the controller. So if I'm defining 1, 0, if I'm looking for a PID controller, as you can see here, I would separate this into a PI controller and S+2 so that I would write down the multiplication basically. Kp plus Ki divided by S in parentheses times S+2 should be a better way of trying to design this. So if I'm in an exam, that would be quite important. If you're in MATLAB, you could maybe use this. It's not that big of a deal. And then we see that the closed loop looks like this, the polynomial looks like this, the set of equations look a bit more different, as I've told you before. P is 3, of course, since we have numerical values, this is 6, 8.86 divided by 100 gives K. 8.86 divided by 2.86 15 times 3 gives some value for z, and you're good to go. Then the whole controller looks like this. And we can see we have this cancellations here and here. No, actually only here. 1 0 is here, 1 pole is here, and then we have this pair here. And this is the potential solution. Then there are also all different sets of solutions, but they are not covered here. And then, as I've told you before, this is the worst way of defining the controller. And I did show you how it ends up being like. Now, you could remember that we could directly conclude what A is. A was basically 5. You can see that the sum of the poles should be 5 in this case. And then the multiplication of the poles of the residual poles would be positive if Ki would be positive. But that direct relation isn't here. So you have to work way harder than that. You can see it's quite nonlinear, and it's a mess in terms of if you have this in an exam, you will consume time, you will waste some time on this. So therefore, this is not an ideal way. Go ahead and use KD, KP, KI and define it like that. Don't use residual polynomials that look like this. Use s squared plus as plus b. If you need a higher order one, just update the order. S cubed plus as squared plus bs plus d or c would be also another good residual polynomial. Yeah, you can see the stability condition gets messed up. You have to write that to get to a point where you can see, oh, it is 0.0286 where the stability starts. It should be negative sign, by the way. So it's quite interesting, in my opinion, and I wouldn't really recommend you to use this PDF way of solving stuff. Here you can see we have the convex combination, so alpha times certain objective index and 1 minus alpha the other one, combine them to just one single objective so we can take the minimum of it. Now we can see by not really gridding the whole grid, because yeah, this is quite old and I've improved upon this in terms of code, we get a suboptimal solution, I would say, because optimally we know that this should cancel and this should be at 5, and this is a little bit lower than it has been here. But you can see the cancellation becomes obvious again in the closed loop, and you can see it's roughly the same thing. In terms of the table that is generated, it looks again more crowded and ugly in my opinion. We have some complex numbers. That's what I want to avoid if I use KD, KP, KI, and AB in terms of residual polynomial coefficients. That is why it is important. And you can see that this is not Z1, the 0 itself. This is S plus Z1 equals 0, or S plus Z2 equals 0. So you have to think about that. So these should be positive to have stability in other terms. You can see that here we are missing some stability. So these are not stable solutions. And step info provides not a number flags for the ones where overshoot or settling time cannot be applied or solved. Then your objective becomes not a number, and the minimum shouldn't give that to you. So you're quite safe in terms of MATLAB. Now you can see that probably this one is chosen as the solution that's being optimal, and you can see almost pole zero cancellation at the origin, almost cancellation at -5, and we have this ideal thing. And you can see it's not really that important if the cancellation is exact, because it still works because it's out of the dominant region, and this is just not there at all, and it's not the system's pole that is going to be canceled. So you can see the code here, which is again not the optimal code here. For the Ziegler-Nichols method, you can see this is basically the same strategy. We've just used the same way of defining stuff, but this is more like it. So Kp divided by 0.5t. What did I do wrong? Kp divided by 0.5t and 0.125t. So what's the issue here? 0.6k. Seems like it is the same. What are the values? Let's check if we're correct. What is KP? 0.42. That's correct. KI. That's not correct. Run 3. Oh, I mixed up KD and KP. This should be KI. Should be KD. No, this should be it. Yeah, that's more like it. You can recognize if it's a root locus, if it's a Ziegler-Nichols design or not, from its shape. It has almost the same damping ratio or overshoot behavior most of the time. And it needs tuning, of course. We have a certain setting time, which we didn't decide upon, and we have a certain overshoot, which most of the time is going to be the same, because shape-wise, it's almost something around this. It has some oscillations, but it is able to track the input because it's a PID controller. So yeah, this is our design point, but we don't have any sort of relation between Ziegler-Nichols and design point because yeah, the method doesn't give us that. It's just a tuning method or starting point for PID design. So in terms of phase lead design, it's still going to be the same. We will define the system, take the closed loop, look at the closed loop, define the set of equations. Since there's a cancellation, we've decided upon the zero of the controller, and then this is going to be the phase lead controller, and it works kind of like it. So because we need some phase lead controller, it works. But for this system, and the reason why we are okay with a PD controller for this specification for this system is that the system's type is already 1. And if we are talking about step type inputs, type 1 systems can track step type inputs. If you want to track ramp type inputs, for example, then designing a PID controller is quite important in this case because it should be a type 2 system. By the way, the type of a system is the amount of poles at the origin or the amount of integrators in the feed-forward path. So that's quite important. In the feed-forward path, the amount of poles at the origin determines the type of the system. And you can see in the feed-forward path, F and G are in the feed-forward path. G has an integrator, F also has an integrator. The overall feed-forward path would be a type 2 system. So if you would design a PID controller that's not canceling its own pole, then you would get basically also ramp tracking. So this system would track its step input and ramp type inputs. Maybe not parabolic types. Therefore, you need to add another one, which is quite hard if you think about it, because we would have S cube at the origin, which is not quite nice. So yeah, and for this same reason, if you design a p-type controller, the system will also track its step inputs because it's already a type 1 system. You don't really need to add an integrator to the system. That's why we didn't get PID controllers right away, because the system was able to track it, and p-type controller looks to be, and the specifications are chosen so that it looks to be sufficient. If I change the setting time, it will mess up everything. The whole point will change. And therefore, in D, when we design a phase lag lead controller, we end up in the reference tracking, which is not always the case, because after designing phase lead controllers, we actually design phase lag controllers to compensate for the steady state error, where this is not present here. And the reason for that is, again, the system is type 1 anyways. So yeah. And you can see that if we drop that and try to design a phase lead controller in its most general form, again, the poles and zeros, they're messed up, and then we need this objective. Here we get a whole different thing. We get 2.44 and 3.989, which should give us basically an almost same effect as the controller that we had before. So you can see it is basically possible to optimize a phase lead controller for this system, but again, in terms of root locus, it is possible to come up with a phase lead controller because of its angle contribution. We are basically looking for something that gets rid of the angle of S+5, so there would be a solution to that, and it would track the reference because it is already a type 1 system in the feed-forward path. So yeah. We've talked about the PID controller in more depth, as you can see, and we've also talked about the phase lead controller. If we're designing a phase lag controller, most of the time the design will end up being in having infinite amount of solutions because, well, we don't want to touch the transients that much. And therefore, in time domain, when we design a phase lag controller, what we do is we just choose the origin, and near the origin, we add a pole and a zero, so that in terms of root locus, the angle contribution, the difference of the angle contribution is not that big. But what we're trying to do is we're trying to compensate the steady state value or error. So the ratio will depend upon that, but the angle contribution should be near zero. So it shouldn't change the angle because we don't want to mess up the point, the design point that we have already established with a P-type controller or a lead controller. So a lag controller is just chosen to be maybe something around the origin, just choose one pole. Sometimes we like to take the dominant pole pair. In this case, it was 1, for example, and 1 divided by 50 would give us the pole, and then you would choose the 0, like 10 times would improve that. So 10 is equal to Z over P, and then you would end up in a 0. These poles and zeros would give you the lag effect that you're looking for. So it's quite an experimental design method in the time domain if you think about phase lag controllers, but phase lead controller can be designed like using the algebraic method. Most of the time we don't use lag controller with the algebraic method. It doesn't mean that you shouldn't, you can, but most of the time that's not the way of doing it. We just add it near the origin and it works magically. So yeah. That's about it for this week. We've covered the PID controller, the phase lead controller, and yeah, we will again talk in more detail about PID control design. And slowly we will progress to more interesting stuff about control design, maybe the structure itself, some control signal stuff, and so on and so forth. And then it will come time where we will look at frequency domain and then state space, and then the semester will be over. So yeah, that's it for this week. See you next week, same day, same hour. Yeah,
Hocam sorum olacaktı.
tabii.
Ama quiz hakkında sorabilir miyim?